Okay, so we defined our area function, and we asked area function should satisfy these three properties, right? First one is this one, and then the second one and the third one. Okay. Now let's see what this will lead us. Okay. Now take pairs of vectors of the form UV1 and UV2. So we have two parallelograms where the bases are the same, or one vector is the same, but the other vectors are different. So how would you, for example, compare the areas of the summation and so on? Well, here is the idea. Whenever I have, let's say, a parallelogram like this, so its area is this much, but we can do the following. I can look at the projection of this second vector onto the first one, like projection of V onto this axis, and we obtain a vector. Of course, that vector is parallel to U, and let's say this vector is just, it's a multiple of U, let's say lambda U, right? Lambda U. And then we know that area of UV is the same as, I'm sorry, area of UV minus lambda U, right? Because of this. If you add a multiple of the first vector to the second one, the area doesn't change. So that's what I do. I just add a multiple of U to V, and I obtain this gadget. These areas are the same. Actually, what you are doing is the following in this process. You keep U the same. So this is, let's say, U. What about this one? V minus lambda U. From V, I subtract the horizontal component. What is left is the vertical component. So this is just V minus lambda U. Therefore, your parallelogram is replaced by a rectangle. Okay. This is the parallelogram, this is the rectangle, and they have the same areas. But this way I can manipulate these areas easily if it's a rectangle. Now, what about these two guys? So I can apply the same trick to this one and this one, and write the area of the parallelogram spanned by U and V is like this: U lambda 1 times U V1, okay, like this. So what I do, this is a parallelogram. Now this is a rectangle. Lambda 1 is what? Lambda 1 is this lambda, okay, whatever it is. And then what about this one, this guy? I can apply the same trick to this one and obtain U and then V2 minus lambda 2 U. So what we have is the following. Let me just draw some pictures. We have the following. Here is my vector U. Şurada tekrar yapayım. Here is my vector U. Okay. So we have the same plane, but I just draw it twice. And here we have this vector. Let's say B1. So we have this parallelogram. And what we do, okay, this is U, and this time I replace V1 by V1 minus lambda 1 V1, lambda 1 U. It is this vector. V1 minus lambda 1 U. So that this parallelogram is replaced by a rectangle. Okay. So they have the same areas, the same heights, the same base. One of them is a parallelogram, the other one is a rectangle. I do the same thing here. Suppose this is my no, not this one. Suppose it is this one here. Let's say this is, so this is U, this is V2. And then we have what? Okay, so this will be just V2 minus lambda 2U. And then we have U here. So we have this rectangle. So instead of this parallelogram, I have this. Now, this rectangle and this rectangle get the same base. I can just put them one top of the other one. So, area of I know this. U V1 is the same as area of U minus lambda 1. No, U, comma, V1 minus lambda 1 U, and 8 U V2. This is 8 U V2 minus lambda 2 U. But these are rectangles, okay? These are rectangles. If I just add these two side by side, I will get up 8 U V1 plus 8 U V2, 8 U V1 minus lambda 1 U plus 8 U V2 minus lambda 2U. But one of them is this rectangle. Let's say this is V minus lambda 1U. And then the second one, so this piece is, let's say, V minus, so V1 minus lambda 1. Okay, V1 will check. and it is B2 minus lambda 2U. Right? One of them is this rectangle, the other one is this rectangle. They have the same base. What is the area of this one? So what is the sum of these two? Right? Since these are just rectangles with the same base, this two areas is the area of this picture. So what is that? It is just A. And then what is the height? Height is just U1 minus lambda 1 U plus U2 minus lambda 2 U. Okay. So this is A U. What is this vector? This vector is just V1 plus V2 minus lambda plus or minus lambda 1 plus lambda 2 times U. Değil mi? Ama burada da ne yaptık? Note that I have this vector U. I just add to this vector a multiple of V. I know that this has no importance in the area. Therefore, this vector is A U V1 plus V2. Okay? Because this has no importance. So what we have seen is that this two adds up to this one. In other words, I can just add these two components whenever these are the same. Okay? If U's are the same, I can just add the V components. Again, this is something similar from tensors, right? Evet.
Nerede olduğunu öğrenebildim mi? Yani bayağı sınıfta bir tanesi olmasını düşünüyorum. Bayağı destek olur.
Evet, anladım. Söyleyeceğim şimdi onu.
Hocam, hyperlinkage, why is
Yeah, it is this property. Where was it? Yeah, this property. Değil mi? Yani if you add a multiple of first vector to the second one, you just bend the parallelogram, but the area doesn't change. You just bend it. Okay? Instead of rectangle, you obtain something like this, or even more. Of course, so we have what? A U V1 plus A U V2, or let me write it this way, the other way around. A U V1 plus V2 is the same as A U V1 plus A U V2. Of course, you know, there is no, I mean, superiority of the first component to the second one. You could just do everything the other way around. Similarly, right, A U1 plus U2 V would be just A U1 V plus A U2 V, right? Yani bir komponent için yaptığımızı diğer için de yapabiliriz. Peki, buradan nereye geleceğiz? Efendim? Bilmem. Göreceğiz. Yani sen şunu soruyorsun değil mi? Göreceğiz. Doğru. Yani her istediğimiz olmuyor maalesef. Efendim? Evet, göreceğiz zaten şimdi. Okay, now, okay, now we have, all right, consider the following. 0 equals A, U plus B, B plus U plus B. This is 0, right? Because the two sides are the same. I have a parallelogram, but the two sides are the same, so it's a just line segment and its area is 0. But I have this distribution stuff, so I can just write it this way. First, let's distribute with respect to this. So this is A, U, comma, U plus B, plus A, B, comma, U plus B. And then I use distribution with respect to the second one. So this is A, U, U, plus A, U, B, plus, for this one, A, B, U, plus A, B, B. Well, this is again 0. This is again 0. So what we see is that hence kamerayı bu tarafa kalmış. En heyecanlı yerinde. Okay, now so we have this. Similarly, we can write down this formula because you just, whatever you have done for the second component can be done for the first component, right? Just rotate the picture 90 degrees. And then we have this, and then we consider the following parallelogram where the two sides are the same. Therefore, this area is 0, but I can use the distribution law with respect to the first component first, and then with respect to the second component. So this 2 is this one, and this 2 is this one. And then we again realize that this is 0 and this is 0. Therefore, the remaining two guys should add up to 0. Okay, so A U B should be the same as this B. So if you want the area function to be a linear object, okay, satisfying all these innocent looking axioms, then you should accept this. Okay, area of the parallelogram spanned by U and B is the negative of the area of the parallelogram spanned by B and U. And therefore, you see that the order of this gadgets is important. So for us, if you are given a parallelogram like this, we should specify which one is the first vector, which one is the second vector. Okay. Of course, you can just say, all right, the area of this guy is just, this area. But if you want to see it as a function, okay, then you have to be more careful. Then you have to specify which one is the first vector, which one is the second vector, because area depends on that. And area can be negative. So that's why naturally area is a negative, is a real number which can be negative. Okay. So area doesn't have to be positive. Ve bu hani sentetik bir şekilde elde edilmedi, değil mi? Yani işte doğal bir takım gözlemlerin sonucu olarak.
Adamın negatif olması yani ne anlama geliyor mesela?
işte söyledim ya demin, negatif olması şu. Uzayda şu alan var. Buradan mesela ne kadar hava geçtiğini, bu ızgara olduğunu düşünün. Hava geçtiğini öğrenmek istiyorsunuz. Ben saniyede 5 metreküp hava geçiyor dersem bu ne anlama gelir? Pek bir anlama gelmez, değil mi? Çünkü yani böyle mi geçiyor, böyle mi geçiyor? Onu söylemek için işte artı 5, eksi 5. Dolayısıyla bir yön seçmeniz lazım. Tamam mı? O yüzden hani alan, uzunluk, hacim, bu nesneler doğal olarak işaretli olmalı. Right? So, area by itself is not a positive number, right? If you think of physically, if you have a region like this, and suppose you want to know how much air flows through this region, it should be a signed quantity because if it is, let's say, positive, then I can think of it as it's going this way. But if the air is flowing the other way around, it should be negative. So this area should come with a sign. Okay?
Hacmi işareti.
Efendim?
Hacmi işareti.
Ne ifade ediyor? Yani matematiksel olarak bir şey ifade etmesi gerekmiyor. Fiziksel olarak sen daha iyi bilirsin ama yani mesela değil mi? Hacim hani antimadde olabilir. Değil mi? Negatif.
Bir şeyde, fizikte de alan vektörü olarak kullanıyordum. Açısı alanı da hacmi işlememiş.
Yani işte her şey pozitif varsa negatif de vardır. Öyle düşünüyorum. Charge olarak düşünüyorum. İşte hani belli bir yerdeki yük artı olabilir, eksi olabilir. Okay, now, of course, we see that, this area function resembles tensors, right? Ne yaptık en son? Evet, şunu yaptık. So, let's compute, for example, the area of the following parallelogram. Let's say U is AB and D is CD. Okay. Let's say E1 is this vector 1, 0. E2 is this vector 0, 9. And we assume that the parallelogram with sides E1 and E2. So let's assume this E1, E2 is +1. You can say it is -1. It's up to you. But let's say this parallelogram, it's a unit square. And by assumption, we know that the area is the product of the lengths. So 1 unit, it will be +1 or -1, right? We don't know whether it's plus or minus, but it's actually up to us. We can determine that. Let's say it is +1. Once you specify this, then you know the area of all the rectangles. Let's see. What is U? U is just AU, but it is just A times E1 plus E times E2. What is V? It is CD. This is C times E1 plus E times E2. So what is AUV? Well, A E1, E2, comma C E1 plus D E2. All right. Using distribution law, I can write this as A E1 C E1 plus D E2 plus D E2 C E1 plus D E2. Well, I can now use distribution law for the second component.
Hocam, instead of distribution rule, can we write, so for example, say C1 is just an multiple of A1, then that's
Yes, it's better. Right. This vector is a multiple of this one. Therefore, I can just erase it. Right? That's what you are saying. Okay. Yani şöyle bir arkadaşım. A1 U2. Tamam mı? If you don't like this, you can write the following. This plus A E1 plus C noise, comma CE1, but I have E1 E1. It will give us 0 because okay, this is A. A will come out, C will come out, and then I will write A E1 E1, but it is just 0. That's why you don't need to write this gadget. So this is just. And the same thing here. This is the multiple of this vector. Therefore, I can just write VE2 and then CE1. Well, then this A comes out. Right, this is A E1 DE2 plus this D comes out. A E2 CE1. But then this D comes out. AD A E1 E2. And then this C comes out, EC, A, E2, E1. So, AUV is then what? AD minus, sorry, AD, A1, E2. A1, E2, by assumption is just 1. So this is just 1. Minus BC, no, not minus, this is plus, but I have here A2, E1. So what is A2, E1? Well, if this is positive, then this is negative, right? So minus 1. So we have AD minus BC. Okay. What is this? This is just, you see, the vector, this was the vector AB. This was the vector CD, and this is nothing but if I write this guys as rows or columns of the matrix, this thing is just its determinant, right? What is the determinant of this is just AD minus BC. So determinants are nothing but actually the objects which gives us volumes, areas, lengths. One-dimensional determinant is length. Two-dimensional determinant is area. Three-dimensional determinant is volume, and so on. Tamam. So both, determinants, and I will now. Next, I will write this as a tensor. These objects are naturally arising objects. They are not artificial things. Okay, now we can also represent a using tensors. Let's see how we can do it. Ya zaten tensörlere çok benzediğini gördük, değil mi? Özellikleri. O yüzden de okey. Bir. Alright. Well, if these are two, and this basis, let's say E1 and E2, E1 and E2, then it's due homomorphisms from R2 to R2, R2 to R, and I have this new basis, right? These are homomorphisms from D to R, and they are defined by the following properties. One star E1 is just 1, E1 star E2 is 0, and E2 star E1 is 0, and E2 star E1, no, E2 is 1. Now I will define the following. E1 and E2 are functions, right? They eat vectors and gives us real numbers, right? E1 eats this one, gives us 1, eats this one, gives us 0, and so on. We can define similarly tensors as linear maps. So for any covectors F star and G star in D star, so namely R2 star or homomorphisms from R2 to R, right? These are homomorphisms. Define the map X star tensor G star. I know what this is, but I want to define it as a map from aslında map demeyeyim de define the action of this tensor product on B cross B as follows. Şimdi bir tane vektör olunca, if I have only one covector, I know how it acts here, right? It just eats it and gives a number, right? Yani, I know this, F star B. And if you give me a vector, I know what this guy does with it. It eats that and gives us a number. What about something like this? It should eat a pair. So F star and G star on a pair of vectors, V1, V2. What should be the result? I will define this, okay? I will define it this way. F star eats the first guy, G star eats the second guy, and we multiply the answers. Bir tane kovektörün ne yaptığını biliyorum. İki tane kovektörün tensör çarpımının ne yaptığını böyle tarif ediyorum. Diyorum ki İki tane kovektörün tensör çarpımı iki vektör yiyecek. It will eat, so the product of two covectors, tensor product of two covectors, like this, S star, tensor G star, will eat a pair of vectors, and this is how it this pair of vectors. The first covector will eat the first vector, the second one will eat the second vector, and I multiply the results. Okay. Now, what kind of object is this? Hani? Bunlar direkt burası direktler. Bunlar these are elements of our field, right? For example, they are real numbers. Whatever your field is, okay? I just multiply these scalars. These are scalars. So in our case, K's maybe in our case it is just R. And we multiply real numbers. Now, okay, now claiming this, our function A, which was defined from R2 plus R2 into R. And I have this gadget, right? This is a same thing. F star tensor G star is a function from B to B, so R2 to R2, and E1 star tensor E2 star minus E2 star tensor E1 star. This is a map, this is another map. The difference is also map from R2 to R2 into R are the same. Nasıl yaparım? Now, this is easy. I know already how this guy acts, right? You know that A of AB, CB, I just computed it, and this is just the determinant AD minus BC. Now let's compute the same thing. Efendim? Anlamadım. Evet. This guy, if I take a vector here, AB, another vector CB, I already computed that this is AB minus BC, oriented area of the parallelogram. Now let's also compute this one. This is also function from this into this. Let's see what is the result of it. Okay, E1 star tensor E2 star minus E2 star tensor E1 star evaluated on the vectors AB, comma CB. Okay, now what is the result of this? Now I have a function minus another function applied to this pair of vectors. What I mean by this minus, I mean the following. This guy applied to this one, minus this guy applied to this one. Now, f minus g x means what? If it is minus g of x, right? If you have minus here, you first apply this guy to this one and this guy to this one, and you take the difference. So this is E1 star, cancel E2 star, apply to this pair of vectors minus E2 star, cancel E1 star, apply to the same pair of vectors. But let's see what this is. Now, I have defined here how this cancel product of two covectors is two vectors. The first covector is the first vector, the second covector is the second vector, and you multiply the results. That's my definition, okay? That's my definition. So let's apply to that definition here. So this is my first covector. It will eat the first one. So E1 star will eat this guy, and then E2 star will eat this guy, minus E2 star will eat AB, and E1 star will eat C. What is E1 star AB? This is A times E1 plus, right? This thing is just A times E1 plus B times E2. So E1 star will eat this guy, will give me A, and from this it will give me 0. So this thing is just the first component of this vector, which is A. This is the second component of this vector, which is B. This is the second component of this vector, which is B, times the first vector of the first component of the second vector. AD minus BC. So this function and A agree on every pair of vectors, right? This function applied to this pair of vectors gives me this, and A applied to this gives me the same thing. Therefore, A can be represented, so hence A can be represented like this. This is E1 star E2 star minus E2 star E1 star. Okay. So we can represent determinant as a tensor. Okay. Süre bitti galiba. Okay. Let's stop. Next time we will continue.